This is going to be our lecture video for December 8th. Let's go ahead and get started with this do now here. We need to solve, include complex roots if there are any. So just a straight up solve problem. Well, let's visit how many solutions we're expecting. So with the highest exponent being a 4, fundamental theorem of algebra tells us that we are expecting 4 solutions. So those could come in the form of double zeros, triple zeros. They could be imaginary, irrational, rational, anything. But if you add them all up, we're expecting 4. So we shouldn't stop trying to solve this until we've come up with all 4. Now the first one is actually really obvious if you think about it. It is the solution x equals 0. There is no y-intercept here. The y-intercept equals 0. So if you're crossing the y-axis at 0, then you must also be crossing the x-axis at 0. Another way to think about this is that I could factor out an x from every single term here. Just take out an x, leaving behind an x cubed minus 3x squared plus 5x minus 15. And then zero product of property says that if x is a factor, then 0 must be a root. All right, so 1 down. We've got 1 root, but we're expecting 4 solutions. So now we got to look at this cubic. We should see if maybe we could do some sort of factoring by grouping, or see if it's in quadratic form. But neither of those are the case, so we're going to start guessing rational roots. 15 doesn't have that many factors, so we'll hopefully find another root here quickly. The numbers we're going to test are 1, 3, 5, 15, -1, -3, -5, -15. All of the factors of 15. So, and I will test these using synthetic division. If this has a rational root, it'll be one of these numbers. Start with the smaller numbers first. So 1, -3, 5, -15. Let's test 1 first. All right, so we drop the 1. 1 times 1 is 1. -2, -2, 3, and we didn't get it. Let's try, I'm going to skip up to 5. So the reason I'm doing that is because, let me finish setting this up. I know that 1 evaluates to be a negative number. If 5 evaluates to be a positive number, we'll know we've got a 0 somewhere between 1 and 5, and it'll likely be 3. If not, then we might guess some other stuff. All right, so I drop down the 1. This is a 5, 2, 10, 15, 75. Add those together, we get 60. So it does cross from being negative to positive, so we know that there is at least one 0 between 1 and 5, so it's likely 3. So we'll try 3 next. 1, -3, 5, -15. Drop the 1, +3, 0, 0, 5, 15, 0. All right, so 3 is another root. The box better. So good, we are up to 2 of these solutions. Not only that, but we have shrunken our quartic down to a cubic, and now it's all the way down to a quadratic. So we're going to take these coefficients here and turn them into a quadratic. X squared plus 0x plus 5 equals 0. All right, now we can just solve this by taking square roots. I'll move the 5 over to the other side. I get now x squared equals -5. Square root, and I get x equals, well, right, is the square root of -5, which we're going to immediately turn into plus or minus √5i. And there are all 4 of our solutions. Let's revisit them again. X equals 0, x equals 3, and x equals plus or minus root 5i. This counts as two solutions because of that plus or minus. Okay, do now part 2. I want to expand 2 minus 5i squared. All right, so first thing about expanding an exponent is to rewrite the base multiplied by itself as many times as the exponent says. This time it is just a 2. All right, now that I've expanded it to that point, I'm going to distribute first, outside, inside, last. I get a 4 minus 10i minus 10i plus 25i squared. But here the special rule about I comes in, that I squared is equal to -1. So this I squared here can be replaced with a -1. And now the expression is 4 minus 20i minus 25. It flips the sign of the plus 25i squared. Combine your constants, but you normally bring those to the front of the expression. Make this -21 minus 20i, so that it's of the form a plus bi, which is how we express most complex numbers. All right, goal for today is to be able to do long division with polynomials. Why we're doing this, we can use this technique to find the roots of large polynomials. So when things like rational root theorem fail us, and we might even test all of the rational roots and not find a single one, long division can help us out. Or maybe there's just way too many rational roots to test. That'd probably actually be more likely the case of why we would need to use it. Okay, so let's talk about simplifying division when the denominator is just a monomial. If the denominator is just a monomial, we're going to distribute this division to each of the terms in the top of the expression. So this here is going to become 2x to the 4th over 2x squared plus 4x cubed over 2x squared. And so each term gets its own 2x squared. All right, we should only try to distribute the division when it's a monomial on the bottom, because now in each of these fractions we're allowed to start canceling. In this very first one, the 2's can cancel. Also, the x squared can cancel with 2 of these x's and reduce that to be just a 2. So now this term here is just an x squared. All right, here this 2 will cancel with 2 of the 4. Well, we're effectively splitting the 4 into a 2 times 2 and then canceling one of the 2's. Or you could just think of it as 4 divided by 2 is 2. X squared cancels that 2 of these x's, leaving only one x behind, so plus 2x. Minus 18 over 2 becomes a 9. X squared cancels with the x squared. Plus an x cancels with one of these x's, but we have to leave something behind on top, so we leave a 1 behind on top, so 1 over 2x. Plus a 2 cancels with 2 of that 4, or 4 just divided by 2 is 2, and we get 2 over x squared. And this is considered to be simplified. This is a type of standard form. Another way to write this would be to use negative exponents for these fractions here. But let's not worry about that this unit. All right, so now we're getting closer to doing long division of polynomials, starting with long division using just numbers. Let's remind ourselves how to do this. The number that is being divided goes underneath a long division symbol, and the divisor goes out in front. And then you move your way down by place value, trying to fit the divisor into what is now the numerator. All right, so I go to the 3 first to say how many times can 4 fit into 3? 0 times. So now you shift one place value down. Now you got 34. How many times can 4 fit into 34? It can fit in 8 times, because 4 times 8 is 32. And now we have 2 left over. We drop down just the 1. How many times can 4 fit into 21? 5 times. With 1 left over, we drop down to 6. 4 can fit into 16 4 times. We have 0 remainder, and the result was 854. All right, now we're going to do it with polynomials. So same setup. What the numerator goes underneath the long division symbol. The denominator goes down here. All right, and now we only focus on the biggest terms as we move our way down this polynomial, trying to see what we need to multiply this guy by to equal this. So we'll just focus on the biggest terms, but then both of these terms will end up being multiplied by whatever we put up here. So what do I need to multiply 2x by to become a 6x squared? I'd multiply it by a 3x. Now I'm going to actually do the multiplication of the 3x to the 2x and the plus 1. I'll get a 6x squared, but I'll also pick up a plus 3x. Put a set of parentheses around this, subtract it away. These should always cancel, and then 7x minus 3x becomes a 4x, and we'll drop down the 2. Now I ask myself, what do I need to multiply 2x by to become a 4x? Well, it's just a 2. 2 times 2x is a 4x. 2 times 1 is a plus 2. If I subtract this away, I will have nothing left. I'll have 0 remainder. Now where's my actual solution? Well, it's what we wrote on top. So this quadratic divided by this linear expression is equal to exactly 3x plus 2, which could be very useful information. Now we know that this quadratic here could be factored into a 2x plus 1 times 3x plus 2. All right. Here we've got one. This one does have a remainder, so I will show you what to do with that, but I will tell you all the ones in your test do not have a remainder. So we'll just see what to do with it though. So divide, we get 4x squared plus 23x minus 16. Dividing that by x plus 5. And I'm moving my way down, asking what do I need to multiply x by to equal each of these terms. So the first one would be a 4x. Actually do the multiplication, I get my 4x squared and a plus 20x back. I'm going to add a set of parentheses around this, subtract it away. I get a 3x, drop down the minus 16. What I have to multiply an x by to become a 3x? Well, just a 3. I get a 3x plus 15. If I subtract this whole thing away, I am left with a remainder. Negative 16 minus 15 would be a negative 31. So what do I do with that remainder? Well, you can just list it as the remainder. That's sometimes acceptable. But if I have to turn this back into a polynomial, I would write it like this. 4x plus 3 plus negative 31 over x plus 5. So you put the remainder back over the divisor as its own term in the polynomial. Okay, so now you've seen it. You won't have to deal with remainders on the test though. Okay, can we use synthetic division to do long division? The answer is yes in very specific scenarios. So right here, if we are dividing by a linear factor with no leading coefficient other than 1, then we're allowed to use synthetic division because this here can be directly related to its root of positive 4. Remember, when you go from a factor to a root, you always flip the sign. And now we just do synthetic division with this root. So 5, negative 19, negative 12, 32. All divided with a 4 out here. We drop down the 5. This becomes a 20. At the column, we get a 1, 4, negative 8, negative 32. Remainder 0. Always like to see that. And then these coefficients here become the coefficients of a new quadratic. 5k squared plus k minus 8. All right. So let's go back to practicing finding roots. And this will require, we can get away with synthetic division on this one. Now, notice I say find all roots. This looks like a really simple problem until you realize, well, if this is cubic, so we're actually expecting 3 roots. I can find one really easily. I don't know how to find the others. Here's how we find the really easy one. Because there's no middle terms here, we can take a cubed root of both sides. First, you have to subtract 1 from both sides. X cubed equals negative 1. Then you take a cubed root. All right, negative 1 does have a cubed root. It is negative 1. We get x equals negative 1. That's because negative 1 cubed does equal negative 1. You can reach negative numbers with perfect cubes. But this just counts as one root. This is not actually a triple root. So what we're going to do is we're going to remove this root from this cubic here, and we're going to see what quadratic remains. And I'm going to do that with synthetic division. Let's turn this equation into the coefficients for synthetic division. It would go 1, 0x cubed, 0x, and then 1 for the constant. And then we're going to put a negative 1 over here. All right, I drop down the 1, multiply, I get a negative 1, add, negative 1, multiply 1, add 1, multiply negative 1, add 0. We knew it was going to be a 0 because this is a root. But now this gives us the coefficients for a quadratic, x squared minus x plus 1. Let's keep that equal to 0. Now I'm going to use the quadratic formula on this. So negative b, so that'd be a 1 plus or minus the square root of b squared, so 1, minus 4ac would just be a 4, all over 2a would just be a 2. Let's simplify this. Now we've got 1 plus or minus the square root of negative 3, all over 2. I don't want a negative inside my radical, so I'm going to pop that out as an I, and I get x equals 1 plus or minus root 3i all over 2. And that counts as my other 2 roots. So I always think this is really a strange problem because it looks so simple. You get the first answer of x equals negative 1 very easily, but who knew that there was these 2 imaginary numbers that could also make this balance? If we plugged in 1 plus root 3i over 2 or 1 minus root 3i over 2, we could get this equation to balance. With this very kind of obscure complex number, it doesn't quite make sense why this really complicated number makes such a simple problem work. But we did the math, and we can always double check by plugging it back in. All right. I think we'll call it good there. I know that was a lot. Come to class with questions, and I'll embed a few more for you to practice right here. All right, have a good rest of your day.